recording. I'm going to start with these first three problems, and I'm going to just run through them because we've done them before. MP3 playlist with 12 songs. How many different ways could I order this? 12 factorial. Okay? It's page 1210. It's 12 factorial. Okay? Which is a huge number. 479001600. Okay? I've just got a certain number of objects. I'm ordering them. It's just 12 factorial. Okay? All right, there are 10 runners in a race. Medals are awarded for first, second, and third place. Well, now in this case, N is equal to 10, and R is equal to 3, right? So I've got 10P3, right? Plug that into my calculator. I get 720. Does that make sense? Is that pretty clear? All right. Next one, there are 9 players on a baseball team. N is equal to 9. R is equal to 4 because I'm choosing 4 different players. It's 9P4. 9P4. It's just 3,024. Does that make sense? Okay. Next. We moved into this kind of stuff where it's probability. Number 5. Now remember, whenever I have probability, the first thing that I start with is this. The probability of A equals NA over NS. Now S is all possibilities, all the things that are possible. And A is what I'm interested in. Okay, so I start with finding NS. Well, NS, let's see, all the things that are possible. Well, there are 11 students on the committee, so N is 11. And I'm choosing 3 of them, so R is 3. So all my possibilities are 11P3. Which is 990. Now to find NA, this is what I'm interested in. Well, who am I interested in? Who are the people? 3 people, Sarah, Jamal, and Mai. So N is equal to 3. I'm only interested in 3 people now. I'm still choosing 3 of them. So it's 3P3, which is 6. Once I have that, I get PA equals NA over NS, or 6 over 990, which is 0.00606 refused. Does that make sense? Okay. Next one. I'll go through the future ones more slowly. It's just I've already done all these before. I'm just doing it to refresh. A swim coach randomly selects 3 swimmers from a team of 8 to swim in a heat. What's the probability that she will choose the 3 strongest swimmers? Okay, well, probability of A, remember I'm thinking NA over NS. In this case, NS is all the possibilities. Well, what's N in this case? I'm choosing out of 8 people. And what's R? 3. Good, I'm selecting 3 of them. So it's 8P3. NS is 8P3, which is 336. Now NA. In this case, I'm only thinking of what I'm interested in. So who am I interested in? 3. Very good, the 3 strongest swimmers. So N is 3, and R still 3. So it's 3P3, which is just 6. So the probability of A, which is NA over NS, is equal to 6 over 336. Okay? What? Oh, sorry. Did I not get the... I got the decimal last time. It's 6 over 336, which is 0.0179. And you could have reduced that to, what, 1 over 56? Something like that? 1 over 56? You could have, but, you know, if I asked you for the answer in fraction form, you definitely want to reduce. Okay? All right. Good question. Now, number 9. This is the one we started with yesterday. Yolanda has 3 each of red, blue, and green marbles. How many possible ways can the 9 marbles be arranged in a row? This is very clearly permutations with repetition. Okay? So how do I do permutations with repetition? It's n factorial over a factorial b factorial dot dot dot, where a and b are the number of repetitions. You guys remember this? So n in this case is what? 9 factorial. Then I've got 3 of red, blue, and green. So that's 3 factorial, 3 factorial, 3 factorial. Plug that into my calculator. Get 9 factorial divided by, and this is what it looks like in my calculator. It looks like 9 factorial divided by, in parentheses, 3 factorial, 3 factorial, 3 factorial, 3 factorial, close parentheses. If you do that correctly, you will get 1,680. Any questions on that? Okay. So that's number 9. Let's take a look at number 11. Number 11 says Ramon has 10 cards, each with one number on it. Card numbers are 1, 2, 3, 4, 4, 6, 6, 6, 6, 6. Ramon is going to make a row containing all 10 cards. How many different ways can he order the row? In this case, what's n? 10. Good. 1 doesn't repeat, 2 doesn't repeat, 3 doesn't repeat, 4 repeats twice, so that's 2 factorial. 6 repeats 5 times, so that's 5 factorial. I get 10 factorial divided by 2 factorial, 5 factorial, which is 15,120. Does that make sense? Yeah? You two on your computers, I really hope you've got something very important that you're doing. No? Yes? No? Yes? Close then. Book?
Yeah.
Okay. All right. Good. I believe you. Look, I'm going to take you at your word. I'll tell you exactly what my pastor told me in church one time. He told, well, he didn't tell me specifically. He told the whole congregation. He said one thing that a pastor he was listening to was telling a story. He said I tell my boys, talking about I was telling his sons, you never, ever, ever, never, ever, never, ever, never, ever get away with anything. So you can lie to somebody. You don't get away with it. God watches everything. He sees it. You don't get away with anything. So I take you at your word.
I don't know if I'm putting that in wrong or if I'm getting a different
10 factorial divided by 2 factorial. Yeah, you put the parentheses wrong. Should be like this. Yeah, alright. Alright. Next. 13. Alright, the letters geometry are on 8 tiles in a bag, 1 letter on each tile. If you select tiles randomly from the bag and place them in a row from left to right, what is the probability the tiles will spell out geometry? Okay, so probability, so I'm thinking PA equals NA over NS. First got to figure out all the possibilities. Well, in this case, it's just a simple permutation because it's just 8 objects, right? So it would just be 8 factorial, but I have to check if there's repetition. Is there repetition? Yes. 2 e's, right? So it's not just 8 factorial, it's 8 factorial over 2 factorial, which is 20,160. Is that clear? Now, NA is what I'm interested in. So what am I interested in? Tyler's spelling out the word geometry. Well, how many ways are there to spell geometry? Just one. So NA is just 1. So the probability of A is 1 over 20,160.
What do you do about how E repeats? Does that apply factors?
What was that?
What do you do about how E repeats the letter E? Does that change it at all?
No, I took that into account here.
But and you don't take it into account?
In NS I do. Excuse me. That's a very good question. Are you talking why don't I take it into account here? That's a very good question. And I was confused on that question. So I take it into account in NS, the fact that the 2 E's repeat, right? Well, you would say, well, in NN, why isn't that 2? Because technically there's only one way to spell geometry, but I could swap the E's, right? Is that what you're saying? So it should be 2, right? But effectively that's double dipping. Okay? What do I mean by that? Well, you're taking it into consideration that the letters repeat here. So you don't want to take it into consideration again here, because then it's like you're taking into account twice when you only need to take into account once. Does that make sense to you? So the best way to think about it is take it into an account in your sample space, and then you don't have to worry about it down here. Is that pretty clear? That's a great question. All right. Number 15. There are 4 female kittens, whoa, and 4 male kittens sleeping together in a row. So you imagine a bunch of kittens sleeping in a row. Bing. Assuming that the arrangement is a random arrangement, what's the probability that all female kittens are together and all the male kittens are together? Okay, well, let's see. Probability. Guys, when you see probability, if I were you, I would just write this down. Right? Then you say, okay, what's NS? What's all possibilities? Well, okay, I've just got 8 objects. I'm choosing 8 of them, right? So it would just be 8 factorial, but I have to check for repetition. Do I have repetition? Yeah, I have 4 female and 4 male. So it's 8 factorial divided by 4 factorial, which is just 70. Now, NA, here, once again, you got to think about it. How many different ways can I order these kittens such that all the female kittens are together and all the male kittens are together? 2, very good. It's either all the females are first and all the males are second, or the converse, all the males are first and all the females are second. You see? So NA is just 2. So probability of A is 2 over 70, which would reduce to 1 over 35, or 0.0286. Any questions on that? No? Okay. That was number 15. Number 17. There are 7 books numbered 1 through 7 on the summer reading list. Peter randomly chooses 2 books. What's the probability that Peter chooses books numbered 1 and 2 in either order? Okay, probability, thinking NA over NS. Okay, number of elements in my sample space. Well, how many elements am I choosing from? What's N? 7. You guys got to pay attention to this, right? Because you see how all these problems are slightly different, right? In this one, I've got 7 objects and I'm choosing 2 of them, right? So that's an NR thing, NPR thing, right? Does that make sense? R is how much? 2. Good. So it's 7P2, which is 7P2, 42. Now, NA, now in this case, I'm choosing the books numbered 1 and 2 in either order, right? So now, how many books am I interested in? 2 books. How many books am I choosing? 2. Still just choosing the 2. So it's 2P2, which is just 4. Okay? I'm sorry, it's just 2. Sorry. Another way to think about this is 1 and 2 in any order. It's either 1 and 2 or 2 then 1, right? There's only 2 possible orders. So you don't have to like go through all this work. You could just think about it. Just realize there's only 2 possibilities. Okay? Then PA is equal to 2 over 42, which would reduce to 1 over 21, or 0.0476 is the final answer there. Any questions on that one? Okay. Continuing on. Number 19. A fan makes 6 posters to hold up at a basketball game. Each poster has a letter of the word Tigers. 6 friends sit next to each other in a row. The posters are distributed at random. What's the probability that Tigers is spelled correctly when the friends hold up the posters? Well, probability of A equals PNA over NS, okay? Number of elements in my sample space. All right. I've got 6 objects, choosing all 6 of them, right? So it's just 6 factorial, which is 720. Okay? Now, number of elements in A. I should check for repetition, but there's no repetition. Number of elements in A. How many things am I interested in? How many orders? 1. There's only one way to spell tigers correctly, so it's just 1. Right? There's 720 different orders that these people could randomly sit in. Right? So NS is 720, but there's only one way that I want them to sit. Right? So it's just 1. So the probability A is 1 over 720. There you go. Does that make sense? Okay. You can see how there's all these different types of problems. You've got to be able to understand them. I got you. Okay. All right. Number 21. If 3 cards are drawn at random from a standard deck of 52 cards, what's the probability that they will all be 7s? There are 4 7s in a standard deck of 52 cards. So probability, so immediately I'm thinking PA equals NA over NS. Number of elements in my sample space. Okay, well, what's N? 52. And what's R? Good. 3 cards drawn at random, that's where my 3 comes from. And choosing from 52 cards, that's where my 52 comes from. So it's 52P3, which is 132600. Let me just check that. 132,600. Now, number of elements I'm interested in. Well, how many cards am I interested in this deck?
4.
4. Why is it 4? Only 4 sevens. I'm interested in those 7s, so n is 4. And what's r in this case? 3. Again, it's 3 because I'm only choosing 3 cards. 4p3 is 24. Probability of A equals NA, which is 24, over NS, which is 132,600, which is 0.000181. Does that make sense? Scott, I think that was it, right? Yeah. All right. Good. So we literally reviewed the entire homework. That's good. Yeah. Sure. All right. So let's move on now. Let's move on. And what we're going to learn now is combinations. Combinations and probability. Okay. Combinations and probability. Now let's take a look. (22.3). What is the difference between a permutation and a combination? That is the question. Well, in a permutation, order matters, and in a combination, order doesn't matter. So what is an example of this? Well, I like to think about it like the difference between playing Scrabble and picking letters and putting them on your tray in Scrabble. You guys ever play Scrabble? Yeah. Versus having a bowl of alphabet soup and just sticking your spoon in the alphabet soup. Okay? So I want you guys to visualize this with me. Here's my bag of Scrabble letters, right? Okay? Here's my bag of Scrabble letters, and here's my tray, right? Here's my tray, whatever. I'm not having a good time with my tray right now, but it's okay. Here's my tray for my Scrabble letters. Sorry. Okay. Now, when you start playing Scrabble, you reach in the bag and you pull out 7 letters, right? Let's say you're pulling them out one at a time. Well, you might have a bunch of letters. First be C, then you pull out another letter, A, and a letter T, and then another letter Z,
Q, Y,
then
X.
Q, and Y, X. Okay? All right? Now, as you pull them out, you're pulling them out in a specific order, right? And so, let's say I forget about the last 7 letters, and I just think about the first 3, right? And I say, well, what's the chance that you pull out the letters, pull out cat in that order, right? Well, the order clearly matters, right? If I pull out TCA, I didn't just pull out cat, right? Does that make sense to you guys?
Yes.
Okay. So the order matters here. So this would be like a permutation because the order matters. Now I want you to imagine that you've got a nice, hot, steaming bowl of alphabet soup. Okay? Okay? So you've got your alphabet soup, and it's got all these different letters in it. Okay? And it's a hot, steamy bowl of alphabet soup. Okay? And you take your big old soup spoon and you dip it in there. Here's your soup spoon.
I like the alphabet. I love soup.
Okay? Okay. It's perspective. It's in front of the bowl. Okay?
Closer to us.
Okay. All right. All right. And you pull it out, and you've got these letters here. You've got A. You've got F. You've got T. And P. Okay? Now, and then there's the rest of the soup. You know, it's not like you just pull out letters. It's impossible. Okay? Okay? Shh. Now, I pull out these letters, and I say to you, well, what's the chance that you pull out P, F, A, and T?
1 out of 1.
Right? Well, you know, 1 out of 1 once it's already in your spoon. But if you're just dipping that spoon in that bowl of soup, you don't know that's going to happen that all the time, right? But once I pull that spoon out, does it matter? Is there any specific order of those letters? No, I'm just asking for a combination of letters. You see that? That's a combination because there's no order. Does that make sense there? Does that make sense? So when you're thinking permutations and combinations, you're thinking Scrabble and alphabet soup. All right? So that's the difference between a combination and a permutation. So let me give you another example, something that we can sink our teeth into. All right. So I'm going to ask for 5 volunteers. 5 volunteers. Go ahead. Yep. 4 more. Isis, you want to volunteer? Okay. All right. Solomon already came. Come on, Ashley. She's looking up here. Nadia wants to volunteer. And Deborah does too. Come on, Deborah. Which are all the people that I just made eye contact with. Good job making eye contact. All right. Now, this is what I'm going to ask you guys to do. I'm going to ask you guys to leave. No, I really am. I really am. Now. Okay. Now, I'm going to ask you guys to leave. And when you leave, listen, you're going to come up, whatever you want to do, you're going to come back in 1 by 1. Okay? But don't rush in. You can choose however you want to do it, but just come back in 1 by 1. Okay? And then you'll line up just like this. Does that make sense? But you have to go outside, and then I'm going to give you 10 seconds, and then I'll tell you to come back in. Okay? All right? You ready? Okay, go. Go. All right. Now the rest of the class, you guys ready for what's really going on?
Oh, yes.
So, So, I'm going to ask, what's the probability they come back in alphabetical order? Right? I didn't want them to know because I don't want to do it on purpose, right? Okay? So, what's the probability they come back in alphabetical order? Keyword order. Okay. You guys can come back in now, 1 by 1. 1 by 1. Very good. And go and line up in your order. There you go. Okay. Very good. Let's give them a round of applause. They did a great job.
You guys failed.
Good job. No? Okay. So the question that I asked when you guys were outside, and I didn't want you to hear it because I didn't want you to do it on purpose, is what's the probability that you guys came back in alphabetical order? Right? You see? So let's see. We got Isis, then Deborah, then Nadia, then Ashley, and then James. So they didn't come back in alphabetical order. That's perfectly fine. It was very unlikely that they came back in alphabetical order anyway. But what's the key here, guys? There was an order. Did order matter here? Did order matter? In the question I was asking, did order matter? It sure did. If they didn't come back in alphabetical order, then they weren't in alphabetical order. The order mattered. Does that make sense? So that would be what? A permutation or a combination? A permutation. Now, okay, now I want you guys all to leave the room again. Okay, leave the room again. Thank you. Get out.
What's happening?
Okay, hold on.
I dedicate my desk. It's good work.
Okay. Now I want you guys all to come back in and sit at those desks. Okay? Okay. However you want, come back in and come sit at the desk.
Carefully, it's a trap.
Let's go sit at the desk.
Gentlemen.
Go sit down at the desk. Sit down, you're ruining it. Okay, that's fine. It's nice that he's trying to trick you in that. Sit down at the desk, please. Thank you.
I like sitting.
Now,
I like desks.
now,
I like sitting.
good job. In this case, I said, okay, I now have these students, these 5 students, in a group, in a desk, okay, in a set. Did the order that they came in matter? No. They chose whatever desk they wanted to. I didn't say this is the first, this is the second. It didn't order. I now have a combination of students here. Does that make sense? The order doesn't matter. At the end of the day, I just have this one combination. Is that pretty clear? You guys good on that? Okay, very good. Okay. Let's give a round of applause for our lovely volunteers. All right, good job, class. I'm highly impressed. The skills, the energy, that goes there, and then there's another one. All right. So, now, let's take a look at this. There are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, or actually, let's think of the first thing. The first thing we did, I was trying to find the probability that they would come back in alphabetical order, right? So it would be PA equals NA over NS, right? NS was all the possibilities. Well, what was N in that case? 5. And what's R? 5, right? I'm choosing 5 people. I only have 5 people, so it's 5P5, which is 120. What was NA? What was I interested in? 1. There was only one possible order, so the probability was 1 over 120. Does that make sense? So this is very similar to what we had before. 0.0083. Okay, that's cool. All right, so that's an example of a permutation. But how do we handle the combinations? Okay, well, how do we handle the combinations? Let's think about it like this. When they were outside the room, I had all those 5 students. I told them to sit in the desks. What's the probability that I ended up with that combination of students at that desk, those desks? Probability was 100%. Those 5 students, they all came in. The order didn't matter, so it was 100%. Does that make sense to you?
No.
Well, was N the same? Yeah. Was R the same? Yeah. But my probability ended up as 1. So let's take a look at it. If I do 5P5, it ended up as 0.00833, right? Or I'm sorry, there were 120 different possibilities, right? When I did 5P5, there were 120 different orders that they could have walked in as. But when I did 5 combination 5, which is 5C5, How many different combinations were there? 1. Just 1. And if you type it in your calculator, you do 5 PRB. The second option right after NPR is NCR. You do 5 C5, you'll get 1 in your calculator. You see that?
Right.
The question is why? Well, it will help you if I show you the different formulas. NPR is n factorial over n minus r factorial. NCR is the same thing, n factorial over n minus r factorial, but I divide it by something else. There's something that goes right here that I should be dividing by. Now a hint there is I go from 120 to 1. So what do I divide by in that case? 120, right? It's not a trick question. I divide it by 120. But I don't have n isn't 120, r isn't 120. How could I get to the number 120 using only n or r?
Well, you do probability then
Hello? Hello? No. Okay. Shh. How could I derive the number 120 using only n or r? They're both the same in this case, so how can I get to 120 using only the number 5 in some kind of mathematical operation?
you do
5 to the 5th power.
you use the probability one first.
It's not like 5 squared or something, right? It's not 5 to the 5th power. It's not 1 over 5 or something. It's 5 something.
5 root.
Not the square root of 5. Say it louder with vigor.
Factorial.
5 factorial. 5 factorial. What's 5 factorial? 5 times 4 times 3 times 2 times 1 is 120. So it's 5 factorial, or in this case, or in every case, more generally, it's r factorial. So to get combinations, it's the same equation as permutations, except you're dividing by r factorial. Okay? Does that make sense to you guys? Is that pretty clear? So combinations, order doesn't matter, and it's the same equation as permutations, except you're dividing by r factorial. All right? So, let's now do an example question. Okay, we've got 7, 9, 13, 16, 18 people in the room. Let's say I ask you how many different combinations of people I could have chosen, right? So how many different groups I could have chosen to go out and come back in, right? The order didn't matter. Effectively, the order that I chose the volunteers didn't matter. They all ended up being 5 volunteers, right? So is that a combination or a permutation? Combination, because the order didn't matter. Effectively, I just chose a group of 5 people, right? So how many groups of 5 could I have chosen from 18 people? Well, in that case, n would be 18, and r would be 5. So it would be 18C5. Honestly, just plug it in your calculator. 18C5, 8,568. So that's pretty cool. Could have chosen 8 different combinations of 5 people from this class. All right? 8,568 different combinations. Okay, now, let me go deeper. Probability, so I'm thinking NA over NS. What's the probability that I chose all girls? Okay, so remember NS we already got. We just got NS. Because NS was all the possibilities, which was 8,568. Right? That's all the possible combinations. But an A in this case is all girls. Well, what do I have to know first? R is the same, right? R is still what? What's R? How many people was I choosing? 5. But what's N in this case?
All the girls.
How many girls? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? So 11 girls. It would be 11C5. You see? 11C5 would be 462. So the probability that I would choose all girls would be NA, which is 462, over NS, which is 8,568. Which would be 0.0539, or approximately 5%. So if I chose completely at random, then it would be a 5% chance that it would be all girls. You guys see that? This is how we work with combinations. Yes, ma'am.
How did you get the 8,560?
Oh, I got this because in this case, N was 18, and R was 5, because that's the total number of students in the room. So it's 18C5 was 8,568. And I got that from the previous thing that I just did. So, yeah. Any questions on this? Does that make sense? Okay. So that's combinations and probability with combinations. Let's take a look at an example in your book. Okay. There are 52 cards in a standard deck, 13 in each of 4 suits: clubs, diamonds, hearts, and spades. 5 cards are randomly drawn from the deck. What is the probability that all 5 cards are diamonds? So probability, so immediately I'm thinking PA equals NA over NS. All right? So I figure out NS first. Well, NS, what's N? How many cards am I choosing from in total? 52, so N is 52. And R is how many I'm choosing. How many am I choosing? I'm choosing 5 cards, right? Does the order matter? If I've got a hand of cards, does the order that I choose them in matter? No, I can shuffle them up in my hand. It doesn't matter. So it's 52C5. Plug that in my calculator. I get 2,598,960. Cool. Now, NA. In this case, now, what am I interested in? What's the probability of that all 5 cards are what? Diamonds. So how many cards am I interested in? Good, 13 in each, so it's 13. And what's R? 5. I'm still drawing 5 cards, right? So it's 13C5. Plug that in my calculator. And I get 1,287. To get PA, it's just NA over NS, which is 1,287 over 2,598,960. Which is 0.000495, or approximately 0.05%. That makes sense? Which is kind of interesting to think about it, right? Drawing 5 cards randomly from the deck, the chances that you get a flush are 0.05%, which means a flush is when you get all the same suit, right? Which means 20 times out of 10,000 or 2 times out of 1,000.
I feel like that's not accurate.
1 out of every 500 hands.
Not for me.
Or 1 out of every 2,000 hands, sorry. 1 out of every 2,000 hands. 5 cards, draw 5 cards, and you get a flush
I probably played like 50 games and I've gotten like 3.
with only drawing 5 cards. That's 5 card stud. 5 card draw is when you discard cards. That's completely different. That makes the probability change a whole lot, right?
Calculate that.
That's harder. Yes, sir.
Do you want us to multiply the number by 100?
No. You keep it like that unless I ask you to. If you want to get the percentage, you multiply by 100. Okay? Are we pretty clear on this, guys? All right, I'm feeling pretty good right now, so I think we leave it right there. And we'll call it a day. What was that? Yeah, if you guys have any homework to show me, you can come up to me now. Thank you, class.